Let's talk a little bit about the stoichiometry of acid-base reactions and also about acid-base titration. So in a titration, the concentration of one solution is used to figure out the concentration of another solution. So you're basically using one solution, you know the concentration of it, and you're going to use that, you're going to leverage that information to help you determine the concentration of another solution. In an acid-base titration, a standard solution, usually a base, is added to a sample of an acid of unknown molarity. And then we use what's called an acid-base indicator, which can have different colors in acid and base to monitor the reaction progress. So we basically are monitoring the reaction with our eye, with the naked eye. So a couple of definitions you should be aware of are equivalence point and end point. The equivalence point is the point where the moles of hydrogen ions from the acid exactly equals the moles of hydroxide ion produced from the base. So the amount of hydrogen ions in the flask is exactly equal to the hydroxide ion in the flask. But what we call the end point, that occurs when there's a slight excess of base and the indicator changes color permanently. So here's an example of what it looks like when you do an acid-base titration. So we have a burette with the base in it, and we know the concentration of the base, and then we're adding it to a fixed volume of acid in an Erlenmeyer flask, and then we have an indicator in there that we can use to determine when the end point has been reached. So as you add more and more base to the reaction, or to the flask, to the Erlenmeyer flask, you can see that there's some pink color down in here. And if you swirl the Erlenmeyer flask around, if you have not reached the equivalence point yet, the purple color will go away. But once you hit the end point here, then you'll see that the indicator will produce a color, and you'll know that you've added a slight excess of the base and you've reached the end point for the acid-base titration. So again, we use accurate glassware in terms of a burette to measure the volume of the base, and then we would use a volumetric pipette to measure the volume of the acid, but we're just determining the endpoint with our eye. So before we get into an acid-base titration problem, let's take a look at an acid-base reaction stoichiometry problem. So this problem says if you have 0.10 molar of hydrochloric acid, and you use that to simulate the acid concentration of the stomach, how many liters of stomach acid react with a tablet that contains 0.10 grams of magnesium hydroxide? So I have a whole plan set out here where we're going to have to start by writing a balanced equation, and we're going to have to convert the mass of magnesium hydroxide to moles, and then we're going to figure out, using our balanced equation, the number of moles of HCl, and then finally we're going to convert to volume using the molarity that's given to us in the problem. So let's take a look at how we would do that. So the first thing we're going to need is a balanced equation. So I'm going to swap my cation and anion. So this is a neutralization reaction because I'm adding an acid to a base. So I'm going to get water plus a salt, and the salt that I'll get in this case will be magnesium chloride, which is soluble. And of course it's a salt because it's comprised of a metal and a non-metal. And then of course I will end up producing some water. So there's my balanced equation. So I know that I have 0.10 grams of the magnesium hydroxide, and I've gone ahead and calculated the formula mass of magnesium hydroxide, which is 58.33 grams per mole, like that. And what else do I have? I have the concentration of my HCl, which is 0.10 molar. So using this information, I'm going to start with the mass of my magnesium hydroxide. So I have 0.10 grams of my magnesium hydroxide. And I know that in 1 mole of magnesium hydroxide, I have 58.33 grams of magnesium hydroxide. Again, I just calculated that formula mass based off of the periodic table. And I know from my balanced equation that for every 1 mole of magnesium hydroxide, I consume 2 moles of hydrochloric acid. So I'm going to plug that conversion factor into my dimensional analysis. So 1 mole of magnesium hydroxide consumes 2 moles of hydrochloric acid. The units for moles of magnesium hydroxide cancel out, and I end up with the number of moles of HCl, which is 0.0034 moles of HCl, but it asked me for the volume of HCl. So this is just a quick calculation. In order to determine the volume of HCl, I'm going to take the number of moles of HCl and I'm going to divide that by the concentration of HCl in moles per liter, and that will give me the number of liters of HCl. So when I take my 0.0034 moles of HCl, and I divide that by my concentration, which was 0.10 moles per liter, I get the number of liters, which is 0.034 liters of HCl. I'm just going to do the quick conversion factor to put that into milliliters. So there's 1,000 milliliters in 1 liter. So if I multiply this number by 1,000, I get 34 milliliters. There we go. So 34 milliliters. Anyhow, let's move on and take a look at another problem. And this one is just a plain old titration problem, very common problem that comes up in general chemistry. So it says here, a 50.00 milliliter sample of sulfuric acid. So right away we see that we must have used a volumetric pipette to measure this because I have 4 sig figs in the volume of my acid. And I titrate that 50 mils of sulfuric acid with a 0.1524 molar solution of sodium hydroxide. The burette reads 0.55 milliliters at the start, and then I end up with 33.87 milliliters at the end. What's the molarity of the sulfuric acid solution? Well, what I'm going to have to do is start by writing a balanced equation. So let's do that. So if I take my sodium hydroxide and I treat that, or neutralize that with sulfuric acid. So I'm going to leave my states of matter out. I end up producing sodium sulfate plus I get 2 water molecules. So there's my balanced equation. Now I want to determine the volume of sodium hydroxide that I used. Now you'll notice that you ended up with a reading of 33.87 milliliters on the burette, but you started with 0.55 milliliters on the burette. So I'm going to subtract that to get the total amount of sodium hydroxide that was used, which ends up being 33.32 milliliters. And then I'm going to convert that into liters just by dividing by 1,000 in my head. So I end up with 0.03332 liters of sodium hydroxide. Now I can use the concentration of my sodium hydroxide, which was given to me in the question, 0.1524 molar. So I'm going to take my volume of sodium hydroxide, 0.332 liters, multiply that by the molarity of my sodium hydroxide. So I have this many moles of sodium hydroxide in 1 liter. And then in order to determine the number of moles of sulfuric acid, I'll go over to my balanced equation. So I forgot to put the 2 in front of my sodium hydroxide. So now my equation is balanced. So I know that I have 2 moles of sodium hydroxide and I consume 1 mole of sulfuric acid. There we go. So if I take a look at my units, my moles of sodium hydroxide cancel out, and I end up with the number of moles of sulfuric acid, 0.002539 moles of H2SO4, sulfuric acid. All right, so to determine the concentration, so I want the concentration of my sulfuric acid, so concentration of the sulfuric acid is going to be equal to the number of moles of sulfuric acid divided by the volume of sulfuric acid, and you'll remember that that was provided in the question. It was 50.00 milliliters. So to convert that into liters, I just divide that number by 1,000, so I'll put 0.05000 liters, right? Because again, it was 50.00 milliliters. So moles per liter gives me molar. So I get 0.05078 molar sulfuric acid. So that's how we used our base, which was sodium hydroxide, which we knew the concentration of, and we did a titration, and we were able to determine the concentration of sulfuric acid.